Hi, so we're doing Pascal's Triangle by Filip and
Alejandro.
So before we start, a little info about its creator. His full name was Blaise Pascal. He was born June 19th, 1623 and died the 19th of August, 1662 at the age of 39. He was a French mathematician, physicist, inventor, writer, and Catholic theologian, and had numerous contributions to mathematics, including Pascal's triangle. What is Pascal's triangle? Pascal's triangle is a number sequence where you start with a 1 on top and continue down in a triangular pattern. To get to the next row, you take the top number and the number beside it, which here would be a 0, and you take their sum and put it beneath. So as you can see here, you take a 1 and another 1 to get 2, and then 2 plus 1 and get a 3, and so on. And this pattern will continue forever. Patterns in the triangle. Pattern number 1, the diagonals. So in the diagonals, you can see that each row has a different pattern. So in the first row, you have the ones. In the second row, you have the counting numbers. In the third row, you have the triangular numbers. And then the fourth row, you have the tetrahedral numbers, and so on and so forth. All these diagonals will go on forever, and they are flipped on each side. So you can have the ones on this side of the triangle and on this side. Counting numbers on this side of the triangle and on this side. All of these will be flipped, and all the patterns are on both sides of the triangle. Pattern number 2, symmetry. As you can see, Pascal's triangle is perfectly symmetrical, with each number being reflected in its spot on the other side. As you can see, 3 and 3 are reflected perfectly across the line of symmetry, which is this blue line, and every other number is reflected as are 3 and 3. If a number crosses with the line of symmetry, it is not reflected, but stays in the same spot it would be. Pattern number 4, exponents of 11. As you can see, every row equals an exponent of 11. For example, first row equals 1, 11 to the power of 0 is 1. The second row is 11, 11 to the power of 1 is 11. The third row is 121, and 11 to the power of 2 is 121, and so on. But when you get to bigger rows, like 11 to the power of 5, you start getting overlaps and double-digit numbers. So you get 1, 5, 10, 10, 1, 5. But what do? You can't keep a 10. So you take the 1 and it stays as a 1. You take the 5 and it stays as a 5 because there's no overlap. You take the 10 and you keep the 0 and 0 stays as 0. But you take the 1 and add it to the previous digit of the next number. So 1 plus 0 becomes a 1. And then you take this 1 and add it to this 5. So 5 plus 1 becomes 6. And then you keep this 1 and 1 plus 1 equals 1. So in the end, 11 to the power of 5 is 161,051.
Using Pascal's triangle. You can use Pascal's triangle to calculate the different possibilities results with different amounts of coin tosses. For example, if you toss a coin 3 times, you can use the fourth row, which is 1, 3, 3, 1. There is only one combination that you will get, which is 3 heads, but there is 3 possibilities that you would get: heads, heads, tails, or heads, tails, heads, or tails, heads, heads. But there is also another combination where you can get 2 tails and 1 head, resulting in heads, tails, 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 heads, tails, 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 heads, and there is only one you can get: tails, tails, tails.
In conclusion, we chose to do Pascal's triangle because we thought it was a really cool concept, and we liked all the smaller patterns and real-world uses that it has. And after researching it even more, it taught us that these mathematical patterns and sequences have real-world uses and are applicable to the real world, and aren't just a series of numbers with quirks in it. And that was really cool to see that math isn't just something that's taught in a classroom, but is actually applicable to the world around us.